now. Okay, so it is a great pleasure to have today Ignacio Reyes, who will be presenting in our ISEN seminar. Ignacio Reyes is a postdoc currently at the Albert Einstein Institute in Potsdam. He has worked in ADS-CFT, in the CFT side. He has some very interesting exact results for two-dimensional fermionic systems and other configurations that can be solved exactly. He has also studied the black hole information paradox and has some interesting results using the island prescription in order to recover unitarity. And today he will be presenting about the information in the radiation. Please go ahead.
Okay, Ignacio, thank you very much for the kind introduction and also for the invitation. It's a pleasure to be here. So yeah, what I want to talk about today is based roughly on these three papers of the last couple of years, particularly this last one, which is quite recent. Okay, so here's a quick outline of the talk. I'm going to start by remembering the relationship between moving mirrors and black holes. And I'm going to tell you very quickly what is the new result that I published recently. And that's an exact result for the reduced density matrix of a particular system. Then we're going to, the rest of the talk is going to be specifically about the physics of moving mirrors in flat spacetimes. Although actually most of what I'm going to say and most of the results are actually valid with some very small modifications for maximally symmetric spaces. Everything's going to be in 2 dimensions in this talk. So we're going to introduce how to deal with free 2-dimensional quantum field theories, and that there's a very convenient tool which goes by the name of the resolvent. And then using that, I'm going to tell you some results about what you can calculate using these techniques, in particular stuff like the Renyi entropies and how you can get a page curve and study the issues of unitarity of information in that way. Then I'm going to tell you a little bit about some work in progress that we've been thinking about, this problem of the back reaction of the mirror onto the quantum fields. And then we're going to talk a little bit about the difference between the classical and the quantum case. And I think this is a very, very interesting direction. And then we're going to finish with some outlook. Okay, so let's start with moving mirrors and black holes. So as a mirror in this talk, I just mean codimension 1 surface where we impose reflecting boundary conditions on the fields. So here for definiteness, the mirror is one of these lines. This is a Penrose diagram of flat space. And then the physical system is going to be everything to the right of the mirror. In this particular case, I'm just showing 2 different trajectories. And we're probably all more or less familiar with the fact that if you have a quantum field theory, and you have something that looks like a mirror, if you shake it, you accelerate it, it's going to produce radiation. This is also sometimes called the dynamical Casimir effect. And it has a lot of applications, even some of them very importantly experimental applications. So in the case of, there is a very close relationship between these moving mirrors and black holes, and this was realized very early in the days of the black hole thermodynamics, already in the 70s. In the case of a moving mirror, or let's say in the case of a black hole, when you study stuff like the Hawking effect, then you don't have so much freedom because you prescribe a background metric and then you do some quantum field theory calculation on that given background. Whereas in the case of the mirrors, you have more freedom in the sense that you can simply choose whatever mirror trajectory you wish and then study what the effects of that are. And there are particular trajectories that reproduce the Hawking effect. Now, the reason why why we're interested in studying these problems is that you can get stuff that reproduce exactly the Hawking, for example, the Hawking process, with the advantage that you don't have to deal with some very complicated gravitational physics or geometry, but rather you just need to deal with some very simple principles of relativistic quantum field theories. Okay, so basically in this Penrose diagram, I'm just giving two examples of mirrors that start asymptotically in the far past. They start static, and then one of them, we'll see why these two examples are important later on. One of them accelerates, receding from the system towards the left and becomes asymptotically null. And we're going to see that those kind of trajectories lead to information loss or non-unitarity. Whereas this other orange one, which follows the first one for a while, but then comes back to a static configuration, behaves very differently, and it gives rise to unitarity. So the idea is that we have this quantum field theory living on the right side, and there's some ingoing mode that is reflected by the mirror. So typically or traditionally, there are two ways that people have studied these problems. So the first one, or one of them, the most early version of it, was pioneered by Fulling and Davies. And it resembles very much the sort of calculation that Hawking was doing. And it basically focuses only on the information of the asymptotic state. So they try to do some calculation of say, Bogoliubov coefficients or whatever, focusing on what's happening here on this future null infinity. On the other hand, there's another approach which started early on with this famous paper by these people in '94, but there were also more people doing similar things. And the idea is to exploit conformal symmetry in the sense that if you do these problems, if you just look at the two-dimensional section of this problem, so you focus only on two-dimensional theories, and then you moreover focus on theories that have conformal symmetry, then there are some quantities that you can compute that are fixed by the Virasoro algebra. The most well-known example is the case where you compute the entanglement entropy, not the Renyi entropies, but the entanglement entropy of a semi-infinite interval. And the reason why you can do this computation easily is because when you resort to CFT or BCFT techniques, boundary conformal field theory techniques, you can do this calculation by calculating or you can extract the entanglement entropy by the two-point function of the twist operators inserted at these boundary points. Now, more recently, the group, quite recently, the group from Kyoto did a very nice calculation where they did a similar thing, but rather than using the CFT tools, they were using an ADS3 bulk to do the calculation holographically. So what's the new thing, or what I did recently is I took a direct route. If you look at the previous two approaches, so they are valid for more general class of theories, but they can only give you some very general statements, or you can compute some very specific things. Whereas what I looked at was a very specific theory, namely a free fermion, but that's a case where you can actually do the exact computation of the full reduced density matrix. So you can therefore compute basically whatever you want that depends on the density matrix for an arbitrary disjoint set of intervals. And this is, well, it's quite interesting that you can do this calculation, because then you can consider stuff like, for example, mutual information, which we'll talk about a bit later, which involves more than one interval. And then you can compare the early and to late radiation correlations and so on. And that's what I'm going to tell you a bit about today. Okay, so what are the things one would be interested in computing from the point of view of relativistic quantum information. So one thing, so there are many quantities that capture correlations in the system. A very well-known, very well-studied quantity, actually, by people like Ignacio at CN is are the Renyi entropies, which are a one-parameter family, so generalizations of the entanglement entropy, which carry this index n, and they're related to the log of the traces of the powers of the reduced density matrix on some region. Then you can study stuff like relative entropy, which measures it's kind of a measure of distance between two probability distributions, or in this case, two density matrices. There are stuff like modular flow, where you define this so-called modular Hamiltonian, which has a lot of properties, important properties in many fields of physics. And this defines a modular flow by conjugation with the density matrix. And something that comes out from the calculation of the entanglement entropy is the mutual information, which, as I was saying, it measures the correlations between two subsystems of a larger system. And there's many other things we could compute, but we're only going to focus on a couple of them in this talk. So, okay, let's now be more specific, and let me tell you what we're actually dealing with. This is a problem of fermions with some coupled to a mirror. So for free theories, or for free bosons and fermions, there's something very nice that you can do to do these computations exactly. And this goes all the way to the 70s, but then it received more attention more recently due to the explicit exact results by Cassini and Huerta for free fermions. So the idea is the following: suppose you want to compute something like the density, like the Renyi entropies. So that involves taking the traces of the powers of some density matrix. So because the theory is free, and because you can use Wick's theorem to transform all the higher point functions into two-point functions, this means that the density matrix itself is completely determined by the correlation function. So this is not true in general, of course, in interacting theories, but it is true in free theories. And you can use that to your advantage in order to do some exact computations. So here, for example, we would like to compute this log of a trace of rho to the n. And it turns out that you can do this computation by definition. And by that, I mean not using the replica trick, which is the sort of more standard technique that people use, which is also fine. You can also use it, but the point is that you don't need to use it here. And you can recast these calculations of the density matrix in terms of calculations purely of determining some functions of the correlation of the correlator. Now here, whenever I show an expression like this, I'm not being very explicit, but here G, we usually think of the correlation function as a complex number that depends on two space-time points. But here, we're thinking of it as a linear operator acting on functions, and it acts via convolution. So it's really an operator. So that's what this sort of equations mean. You need to take the log and the trace of a specific operator. And there's this very beautiful way to deal with these kind of problems in math, which is essentially to use Cauchy's integral formula. And the story is very simple. It's the same that you would do for a complex number, but you upload this, or you upgrade this thing to the case of operators. So the idea is that if you have an operator that is well defined, or I mean that it has whose spectrum, so whose eigenvalues lie on some compact subset of the complex plane, like in this particular figure here. So if you imagine that lambda here is, this lambda stands for the eigenvalue of the operator G. So if the spectrum lies in some compact subspace here, then for a given eigenvalue, certainly this formula is true if the gamma is a curve that encircles that eigenvalue, but it's also true for the full operator if gamma encircles all of the eigenvalues. So basically, if you want to compute something like what we had here, this log of this particular function, you can just use Cauchy's integral formula. And of course, the challenge of the name of the game is to compute this inverse operator here, 1 over lambda minus g, which is basically something like inverting the correlation, the operator itself, and that's known as the resultant. So you need to find the operator that satisfies this equation. It's the inverse of this thing over here. And once you have that operator, you just plug it back into the contour integral, and then you basically have, basically you get the spectral decomposition of whatever function that you want. In particular, this one for the Renyi entropies, but as I said before, if you want the modular Hamiltonian, the modular flow, etc., you can consider different functions. So finding this resultant is in general a pretty hard problem. And in one of our previous papers, we developed a sort of systematic way how to approach this problem, which ended up being extremely useful, actually. So this is, I think, all of what I'm going to say about this technical part, but if anyone has questions, just please interrupt and go ahead. The idea is that now, I'm not going to tell you how we did this calculation because it's rather technical, but now if you believe me that you can go through this procedure, this recipe that we found, and compute this resultant and then plug it back into the integral and do these computations, now I'm going to tell you what the result is. Okay, but before that, I need to explain you what calculation I'm trying to do. So what's the physics setup? So here I'm parameterizing the mirror trajectory, which is always time-like in these examples. In null coordinates, as x plus is a function that I'm calling little g of x minus. And in principle, this is sort of like a God-given curve. It's the mirror trajectory is fixed a priori, and we just consider it to be input data. Why are we going to choose a particular trajectory? That's a different question that we can talk about later. But for now, let's assume that the curve is simply chosen. So if there was no mirror, the left moving fields and the right moving would have no correlations whatsoever, and therefore the 2-point function, which is now a matrix, right? Because we have these two sectors. In that particular case, it would be diagonal. The off-diagonal terms would cancel because there's no relation between the right and left movers. These are the plus and the minus. We would just have to deal with the diagonal pieces, which means that we just need to think about a single sector because they don't interact at all. The interesting thing about having a boundary is that now the boundary correlates the two chiralities by obviously the boundary condition. So now in the problem we have to deal with, the off-diagonal terms are not zero, and you have to actually do all the computations for this 2x2 spinner matrix, where these off-diagonal terms are different than zero. And that's very, very important because, as we'll see in a second, this means that there's entanglement between the left and the right movers. And that shows up in the entropies. So basically, that's the physics. In this diagram on the right, I'm just slicing the space. At some point, you need to choose foliations. And here I'm just choosing them to be at constant coordinate time. And then on each Cauchy slice, you choose a given region of space-time, sub-regions of that Cauchy slice, where you trace out the complement, and that defines a reduced density matrix whose entropies, for example, we wish to compute. Now, if this, how should I say this? depending on the mirror trajectory that you choose, this gives rise, of course, to different kinds of physics, but in particular, it also means that if the physics, so if the mirror, for example, was static, then typically which is one of the things you for example, impose when you're doing boundary conformal field theory. In those cases, what you require is that there is no exchange of momentum between the mirror and the system. In this particular case, because we are going to allow the trajectory of the mirror to be arbitrary in principle, this will imply physically that in these examples, there will be energy injected to the system or extracted from the system, depending on what the trajectory is. So there will be this, typically there, what you do is compute the expectation value of the renormalized parallel perpendicular component of the stress tensor. And here, instead of vanishing, in general, it will not vanish, and it's simply determined by the anomaly in 2 dimensions. Okay, so that's the setup. So I told you what's the physics, I told you what's the math method that we're using, and now I'm just going to tell you what the first result is. So this is a result for the Renyi entropies. And here I'm just giving an example for a single interval, AB, at some constant time Cauchy slice, but leaving the trajectory of the mirror to be arbitrary. So moreover, in this formula that I'm giving here, what I'm considering to be the incoming state from past null infinity is simply the vacuum. We can change those assumptions, and in the paper I have the general formulas, but I'm just giving the example for the vacuum. So we have an incoming vacuum state that is going to scatter with a mirror of some arbitrary trajectory, and then I want to compute the Renyi entropies of a single interval AB. So what's the result? That's the formula over here. The first thing you notice is that the dependence on the Renyi entropies on the index n is given by an overall factor here. Now this is in general not true, but in this very simple action, it's usually the case. But the most interesting part of the physics is contained, of course, in here, is the way how the entropies depend on the information of the mirror. So here I separated it in a way that is more obvious to read for people that have some familiarity with this. So the first term here is what you would interpret as the standard term that you get from the universal sector that only depends on conformal symmetry. That's the sort of Cardi-Calabrese result, so to speak. Here, delta is the UV cutoff. Of course, these things are divergent in the UV. But then we see that it depends on the mirror through the position and velocity only at the null projections of the interval. So if this is the interval AB, what this formula is telling us, forget about the details, but it only depends on G and on G prime on these points, on the null projections of the boundary points on the mirror. So it doesn't depend on any other information about the history of the universe or the state or the mirror whatsoever. It only depends on what's happening on these points locally. And moreover, it only depends on the position of the mirror there, given by G, and its velocity there, given by essentially G prime. So it's very nice that you can find a closed analytic formula for this, but I think the real importance of being able to show this is that it gives you, at least for this example, a clear, it makes precise what are the conditions in order to ensure unitarity. Because if you look at this formula, as I just said, it depends only on what the mirror was doing on these null projections of the endpoints. So that means that if, suppose we consider what was happening, the entropies, or what the quantum state was of the fields at some time t1 and then later at some time t2. So if the position if the position and velocity of the mirror at those 2 points were, by whatever reason, are the same as those at the previous time, so if these 2 things are the same at T2 and T1, then this means that all the Renyi entropies at T1 are equal to all the Renyi entropies at T2 at each end. And that, by definition, means that the 2 density matrices have the same entanglement spectrum, or that the same eigenvalues. And that means that the density matrix of the future is related to the density matrix of the past by a unitary transformation. What you need in order to ensure unitarity, to have full unitarity, and not just an evolution that is consistent with or not inconsistent with unitarity, is that you need that, you don't just, it's not enough to have a page curve for the entanglement entropy, which is one of the things that people have been discussing a lot the past years in connection to this island prescription. People usually focus on entanglement entropies, but if you want to ensure unitarity of a system, you need to have a page curve for every Renyi entropy. So I think that's one of the important sort of physics messages that you can take away from this.
Sorry, I have a question regarding that.
Yeah.
I mean, it is like a crucial, assumption, but of course it's known, right? It's a crucial result. In order to derive or to argue that you have to have a page curve-like behavior for entanglement entropy, the fact that entanglement entropy is complementary, right? Like that if you start from a pure state, it obeys the complementarity relation that the entanglement entropy of a region is equal to the one of the complement, right? But the Renyi entropy doesn't have that property, or it does?
I don't know. But in any case, okay, I don't know if it has property. I don't think so.
I think it doesn't, right? But the point is that then what guarantees you that you will have a page curve behavior? Because the point is that, okay, like, I mean, you should think that, let's say if you are thinking about the black hole entropy, then you say, the black hole is implemented by some area of an object that it is physically shrinking. So of course, it is a decreasing function, but then the point is that the entropy of the traced out degrees of freedom, which are still kind of inside the black hole, has to be equal to the entropy of everything that was radiated, provided that you started from pure state, because like the entropy of the radiation has to be always equal to the entropy inside the black hole.
Okay. Good point. So here I am not, this is a very good point, and I think I mentioned it somewhere in the paper. Here, I don't need to assume, I'm never assuming that the incoming or that neither the incoming state or the full state is pure. So in this particular example, that I said that I was scattering the vacuum state, which is a pure state. But actually, the same thing carries through if you scatter, if the state that you send in from infinity is actually a thermal state, which is mixed to start with. So you can do the same analysis for the Renyi entropy starting from a thermal state, which is mixed, which does not satisfy, not even for the entanglement entropy, this complementarity condition.
Okay, yes, this is true, but then, because the point is that the fact that you have a firstly increasing but then decreasing function for the entropy of the radiation precisely has to do with the fact that there is a constraint, right? That the entropy remaining inside the black hole has to be always equal to the entropy radiated away. And the reason for this is that you have the complementarity between what is still inside the black hole with respect to what's outside. The fact that the entropy of the region is equal to the entropy of the complement, because it's like you're tracing out the modes that have already been that haven't been radiated by the black hole yet. So you're tracing out the inside of the black hole. So otherwise you don't need to have this behavior that you have a firstly increasing function, but then at some point after the page time, it has to start decreasing again. So the reason for this behavior is the fact that the entropy of the radiation has to be always related to the entropy of inside the black hole, and they have to be equal. This is how I understand it.
In Renyi entropy, it happens the same. I mean, it is the same, but the Renyi entropy inside alpha with the complementary, but based so they have exactly the same property, of course, with the only constraint that the unitary transformation that you are going to make it is localized actually in the wedge of the region alpha, for instance. In principle, what happens in tactic entropy happens in Renyi with respect to the complementarity as well.
Okay. I wasn't sure about this. I thought.
Yeah. It is true. It has to do with, because at the end this always has to do with how much does it change the eigenvalues of the density matrix under unitary transformations. And in principle, they are preserved if you have a unitary transformation in the Hilbert, if the unitary transformation is an operator localized in the Hilbert space of alpha. So in principle, the same happen. Of course, this will change. This will change if if of course your unitary operator is not localized in alpha or in alpha C, but in the complementary. But it is true for Renyi entropy as well, the complementarity condition.
That the Renyi of the region is equal to the Renyi of the complement?
Yes.
Okay.
Yes.
Mm-hmm.
Okay, thank you.
Okay. Mm-hmm. Good. I think, I mean, what I'm trying to say here is that in this particular example, you can show that this is true. You can actually do the computation and show that, and with that computation, you can make precise the conditions under which you have a unitary transformation.
Okay, I see. So basically, you're showing that that's the case explicitly for the 2D theories that you consider, because you can solve them. Right.
Yeah,
okay.
yeah.
I see. Right.
I'm not using any complementarity condition, although the problem might be phrased in those terms.
Right. I see. Okay. Thank you.
Actually, I would like to understand that better. Maybe we can come back to that at the end. Okay, so what I want to do now is to show you some applications, some examples of this result. So basically, the examples are very simple. We look at, so here's the Penrose diagram. Again, we're going to consider some trajectories that become asymptotically null. Some of them don't. And the idea is that we're going to have some incoming state coming here from past null infinity. Again, this doesn't need to be the vacuum state. This can be a mixed state, for example, a thermal state. And then we can simply compute exactly the density matrix everywhere, in particular that gives the outgoing state. And notice that, well, what should have been clear from the previous transparency is that unitarity doesn't mean that the outgoing state is equal to the incoming state. It means that their spectra, that the eigenvalues are the same. For simplicity here, I'm going to restrict to mirrors that are static in the asymptotic path, so you can actually sort of define easily what you mean by the incoming state and so on. Okay, so what are some particular examples? The simplest thing is just to put a static mirror that doesn't move anywhere. And if you do that, that implies that you can impose conformal boundary conditions. So in that case, this parallel perpendicular component of the stress tensor vanishes, so there's no energy being extracted or injected into the system. In that particular case, if you replace the mirror trajectory into the previous formulas, what do you get? Well, you get this thing over here. So this stands for the Renyi entropies in the right half plane. Again, the same n dependence as before. We have the standard universal piece, which here I'm identifying with a no boundary calculation. So that's the result that you would get in the absence of a boundary. So if there was no boundary, if this was just the plane, this would be everything. And this is the universal result. But when you have this static mirror, you get this extra contribution. And this is really the new piece here that takes this form, where R is the ratio between B and A, which are the two endpoints. So this is entirely the contribution coming from presence of the boundary. Now notice this results match perfectly with a similar thing that was done by Tony and Minchev using a quite different method. So there are three things to be noticed here about this new term that is due to the presence of the boundary. First, that is negative. So it lowers the entropy with respect to what it was without a boundary. It goes to 0 if you take R to 1. So if B becomes very similar to A, namely if the interval becomes very small, then the contribution of the boundary goes to 0. And that makes perfect sense, because if the interval is very small, then the effective length that you see towards the boundary becomes very large. So these effects should die away, and they do. And then it becomes very negative when R goes to infinity. That means if you take this interval and start stretching it more and more, this extra contribution to the entropy just becomes, it diverges, just becomes very negative. And I think the most important of these three, I would say, is the fact that it is negative. And this for me is still a question that I think is a very interesting thing that I didn't make very precise in the paper, apart from doing this simple observation, is that this sounds very much like a sort of version of the monogamy of entanglement, but in quantum field theory for a continuous system. So you're probably familiar with this idea of that entanglement is monogamous. That means, if, for example, if for a qubit system, if you have two qubits that are maximally entangled with one another, then they cannot be entangled in any way with a third qubit. So that's to say, like, entanglement is a resource that you cannot share in an indefinite way with everyone. And there are, and it's something super important in quantum information theory and quantum computing. But typically it's something that is discussed in low dimensional, finite dimensional quantum systems. And in this particular realization, why am I pointing this out? It's because what you see here is that if you have no boundary, as I said before, the left and right movers are completely decoupled, and you get this entropy. Now, if you put a boundary, the physical effect that has is simply to entangle, to correlate the left and the right movers. And the effect that has is that it lowers the entropy, because this term is always negative. That means that, and the interpretation, there seems to be an interpretation in the sense that the left and right movers now have to be less entangled with the rest of the system, because they became entangled with one another. And that sounds very much like the monogamy of entanglement, but for now this is sort of a suggestion, and I don't have any rigorous thing to say about it. But I think it's a very interesting idea. In particular, well, yeah, so you can, if you do the calculation for thermal states, actually, just to write it a bit more explicitly, this makes the difference between two states. So if you take away the mirror and you put a thermal state, this is the state that most people in the literature consider. It's the universal one whose results are fixed by conformal symmetry. In that case, what you have is that you put the left and the right movers at the same temperature by hand, and the global state is simply a tensor product of the two sectors. In that case, the correlation between the left and right movers is vanishing, and that gives you these standard universal results. The state that I'm considering here, which I think is more interesting in this sense, is something that looks like this, that does not factor between the two sectors. There is correlation between the left and the right movers, and the results are non-universal. Therefore, you need to study them with more, with other tools, namely the one that I've been showing here. Another example is more closely related to the black hole evaporation process. So in that case, what you take is a particular mirror that is, the standard Fulling and Davis story. It's a mirror that recedes, so it accelerates and becomes asymptotically null. And you can show that this thing takes an incoming vacuum state and transform it as a outgoing thermal state. Now, Fulling and Davis pointed out, of course, that there's a very interesting suggestion that you can make a conformal map from this space-time to something that looks like this, where you straighten up the mirror trajectory. You can always do that. So here I have this trajectory in blue that is mapped to sort of the origin of coordinates in this other diagram. And this part of the future asymptotic, null infinity becomes what looks like the horizon of a black hole that formed from collapse. But of course, when you play these games with the mirrors, what is absent in the discussion is the black hole interior, because the space-time sort of just ends at the horizon, and you cannot continue it, at least in any obvious way. So you can also, you can also do the computations here. You can also compute the entropies and so on. I'm going to show you a little result in a second. The third and last example is something that I'm not completely certain that has been, it's much less discussed in the literature, but I think it's super interesting. It's simply a mirror that accelerates with constant proper acceleration. Namely, it goes along a render trajectory after the static piece. And the interesting thing here is that if you look at the remote past, what you have is that the mirror is static. So the state that you have is this entangled state that I told you before, where these correlations do not vanish. And what you get is the entropy that I showed you before, containing this extra term that lowers the entropy. But what's super interesting is that in the future, in the asymptotic future, you can show that actually the state that you get is precisely this other state where all the correlations between the left and the right movers disappear. They just go to zero. And therefore, the entropy is given by this universal term. So in this particular example, you can see that it actually, the mirror, although it's not producing any kind of radiation, the mirror is taking one of these vacua and transforming it into the other vacuum. So it takes this state where there are correlations, there is entanglement between the two chiralities, and it erases completely all of that quantum correlations, and it transforms it into a state where you have this tensor product. And of course, this process is non-unitary because you're going from a state that had more quantum correlations to a state that has less quantum correlations, and that's, almost by definition, non-unitarity. And interestingly, this kind of trajectories are related not to black holes of finite temperature that emit Hawking radiation, but rather they're related to extreme black holes. So from this, you can do these calculations of the entropy and find a page curve. So one thing that is, I think, very nice is that people typically talk about page curve of the page curve at the entanglement entropy, but I think it's very interesting to look at mutual information, because then you can actually measure the correlations between the early and the late radiation. And moreover, mutual information is something that is UV finite, whereas the Renyi entropies are all infinite, they don't exist basically. Well, you can regulate them, of course, and they're super interesting, but they're not well defined in the UV unless you use some procedure to subtract the infinities and so on, which Ignacio's worked a lot on. It's not just UV finite, but it's also finite when you take one of the intervals, one of the endpoints to infinity. And the nice thing about doing that is that you can actually, if you look at this diagram here, if you take this point all the way to space infinity, you're capturing all the early radiation. So basically what you can do is to find a page curve for the mutual information, and it's going to look something like this. For these trajectories that come back to the original state of motion of the mirror, you're going to get some mutual information that does something interesting, but then eventually goes back to its original value. Whereas for these other trajectories that become asymptotically null, you'll see that the final, the future mutual information is lower than the original one. In other words, there was a loss of correlations in the radiation. And this thing is sort of, it has many close relations with the quantum extremal islands discussions. Okay, so in the last 5 minutes, do I have 5 minutes?
Yes, yes, you do,
Yeah?
for sure.
Okay, cool. So in the last couple of minutes, I want to tell you not about published results, but about something that is work in progress. And I think it's super interesting. And it's the problem of what happens if you take into account the back reaction of the mirror. So until now, I said that the mirror was moving along a prescribed trajectory. Why? No one knows. We just choose it. But what if we consider the case where the mirror trajectory is determined by some dynamical physical principle? So what could that be? The simplest thing you could think of is to think that the mirror is a massive particle, possibly relativistic particle, and it follows its own Newton's equation, F equals ma. So you're going to have this field theory that is coupled to this massive particle, and they can exchange energy and momentum through Newton's law. So you can study a classical field theory coupled to this problem. That's already interesting, but that's a completely classical problem. The interesting thing is, of course, if we do quantum field theory on the right of the mirror, and this is very much, you know, what is meant by this dynamical Casimir effect. The interesting thing here is that if you, in this particular case, if you accelerate a particle, it's going to generate radiation and therefore suffer backscattering from its own. So it's going to generate a force that is going to the so-called jerk that is proportional to the derivative of the acceleration. So this problem, which we're going to consider in a two-dimensional quantum field theory coupled to a massive particle, it's very analogous to the problem in classical electrodynamics of the Abraham-Lorentz force. This is the thing that comes from this Larmor effect, the fact that a charged particle radiates when it accelerates, and then you need to take this into account when you do the calculations. So it's analogous to this, but it has a different physical origin. And by the way, it's super interesting to learn how actually this Larmor formula actually is used to, for example, it's the way how the Yagi-Uda antenna works. You just accelerate electrons along these wires, and then these create particular waves of particular frequency, and then you have to tune them so that they, interfere destructively on one side, and then they interfere constructively on the side where you want to send the signal. So it's very nice, neat classical physics, but now we're going to consider a very similar effect, but which has a quantum origin. The cool thing about this, I think, is that the space-time where the physics is happening is not something that now is determined a priori, but it's determined dynamically because it depends on the curve of the mirror. So a very, very beautiful model for this was done in this paper by Chung and Verlinde back in the 90s, where they consider a 1 + 1 dimensional quantum scalar field. And in that case, this extra force, so this force over here, the one that goes with the derivative of the acceleration, comes simply from the anomaly in 2 dimensions. So that's basically the same setup that we're thinking of. Now, this physics has certain issues that we have to deal with. For example, that and this is very well known from a century, essentially, is that this involves solutions that have signals traveling faster than the speed of light, coming from the future. So you have to deal with those issues, and also it leads to singularities, which in the original paper by Verlinde and Chung was interesting because they were looking at these 2-dimensional dilatonic gravity theories. They wanted to find, in a certain sense, singularities. And basically, the summary of our work in progress, together with the results by Chung and Verlinde, is that it seems that in this particular problem, although you would expect that maybe, you know, you would have some stable vacuum solutions that would do some reasonable thing, what actually happens is that almost all of the solutions are sort of runaway solutions that are not very well defined. So when you solve the equation of motion, you get stuff like this, where you have a particle that has a tiny acceleration in the far past, and then it just starts accelerating, radiating negative energy, and it becomes asymptotically null, and therefore it has to radiate an infinite amount of negative energy to get to the speed of light. So that's kind of, it's weird. It's not a stable solution, or at least it doesn't seem to be. And then you have even more singular solutions, which are cases where the massive particle becomes null, but at a finite amount of proper time, and it creates a singularity in finite time. So those are even worse. Presumably, you have to sort of cut the space-time there at that point. But until now, we're not very sure what the interpretation of these solutions should be. So what I was expecting, but maybe this was a prejudice from my side, is to find something like damp solutions, where you have a particle, then you give it a tiny acceleration, and then it accelerates, it radiates a bit of energy, and then it comes back to sort of a non-accelerating trajectory. But until now, we haven't been able to find those solutions. And the issue with this is that these two solutions that are sort of not very physical, for the same reasons that I talked about in the previous part of the talk, they always give rise to information loss. So they never lead to unitary processes. So that's a big question. Like, how can we recover unitarity? And that leads us to this. The last thing I want to say is that if this is a proposal that we're exploring, what if maybe the solution is to take into account a quantum back reaction? So until now, what we're doing is taking, in a certain sense, is very similar to what you do in semi-classical quantum gravity. So you take a fixed background geometry, and then you do quantum field theory on that fixed background. Here, what we're taking is sort of a fixed but dynamically determined sort of a classical boundary trajectory, and then do quantum field theory on top of that. This is exactly what we're doing. It's the energy of the relativistic particle plus the energy of the field is some constant, where the field is quantum. But what happens if we quantize now the point particle, the mirror itself? And I think this has never been done. So the mirror, instead of following a given trajectory, what if we integrate over all trajectories? And for each trajectory, we have the quantum fields. So we would sum over all these histories, and basically we would have a partition function that would look something like this, where we sum over these trajectories gamma with the relativistic action there. And for each one of those, we would do the path integral over the quantum fields. So in a certain sense, this sum over world lines is a sum over spacetimes, because the world line is the boundary of the spacetime. The metric is fixed, it's flat everywhere, but apart from that, we have to face this issue of summing over different spacetimes. So I think that's kind of a nice thing. It's what Claudio Bunster calls in one of his papers, I think, something like quantum gravity in 0+1 dimensions. And the big question is whether this procedure will restore unitarity or not, because then we would have a fully quantum system, and I would expect that thing to be unitary, but this is something that we have to work out. Okay, so I'm going to just give you the summary, and I think I'll stop there. Thank you very much.
Thank you very much, Ignacio, for your very nice seminar. So are there any questions from the audience? So I have a question myself. Right, so there's something that interested me, but I didn't fully understand the logic, because, okay, so you say that in the case of a mirror that has an asymptotically null trajectory, it behaves analogously to extremal black hole, right? And I understand why.
Let me go back to so that we this one.
Right. And basically the point is that it doesn't radiate, right? So it is okay. It has a, I mean, because it cuts certain correlations, like it destroys certain correlations, right? Because it destroys certain correlations, it will induce an entanglement entropy because you're tracing out essentially the non-diagonal correlation, so this G plus minus. But because there is no radiation, it has entropy, but it doesn't have temperature. So in that sense, I understand that it would be analogous to an extremal black hole. But usually, when you have an extremal black hole, you have some sort of like some sort of BPS condition that has to be saturated in order to have the black hole, right? Like for instance, you need to have, let's say, more than one charge such that both of them contribute, or more than two, but two or more charges such that they all contribute, for instance, to the temperature in a way that the contributions cancel out, so that you get zero temperature, but you have some charges. Like, you know, in the case of Kerr, it will be angular momentum and mass. In the case of Reisner-Nordstrom, it is charge and mass, and so on and so forth, right? But you have some sort of BPS condition that is saturated. But here, you don't have this, I mean, at least I don't see which parameters you have to play around in order to kind of cancel out the temperature without canceling the entropy. So I just wanted to understand what is the extent of this analogy. You see what I mean?
Yeah. I mean, I must say that this is something that I haven't done much progress on this. I mean, I haven't worked specifically on this particular relation. I know that, I mean, I know papers, I know references, but they actually do this. Of course, they're not doing what I'm doing here, but they make this point of the relationship between asymptotically, so mirrors that have asymptotic zero acceleration that become null but have zero asymptotic acceleration, and extremal black holes. In this particular case, I think the details of what you're asking are somehow not, what I'm talking about here is too coarse-grained to see those details, because if you go back to this case, so in this example, right, the acceleration of this mirror is what determines the temperature of the outgoing modes. This is not a Rindler trajectory. This is one where the acceleration has another particular function. This is the thing that mimics the Hawking radiation.
Right.
Now, if you take this thing and you send and you take that the beta, so this trajectory has an associated beta, namely the one that will be the inverse temperature of the outgoing modes. So if you take that beta to zero, and I think this is maybe the point that what you're making, if you take smoothly that beta to zero, what happens to this trajectory is that it simply becomes a straight line. So you cannot get this sort of Rindler mirror, or at least I don't know how to do it. You don't get the Rindler trajectory by taking the zero temperature limit of this thing. In this particular case, I simply prescribe the Rindler trajectory, and I know that that has a zero temperature associated with it, but which is not the limit of something else. So at this level, I don't know how to tweak the charges of the whatever corresponding system would be in order to find the solution. You know, it's something like, I guess, yeah.
Right. I mean, the higher dimension. So the standard higher dimensional analog of that is the original Cassini-Huerta-Myers kind of sort of computation, right? Like you say, you have some region that you're tracing out, like the usual ball-shaped entangling region, and then you have like a conformal transformation with which you can deform the geometry in order to map that into a black hole. Here, basically, this is the standard thing that you do in Riddler, that you can think of the fact that you're having like an interval, like a half line, and you're basically cutting half of the space, and then you can do a conformal transformation to map that into like a thermal state that would be the analog of the black hole, yeah. Right? So here is what you're doing is like the same as standard, right? But here you're doing the same, but with a moving mirror. So it is some trajectory, right? Like it.
But actually, notice that what I'm doing here is very different to what Cassini and Werther-Myers are doing, because in their case, what they have is that the full density matrix is defined on the plane, for example. Can also be the symmetry, but let's say the plane. And there you take a ball-shaped region, and then you do a conformal transformation to map that to whatever, say Rindler.
Right.
But in that case, the thing that is associated to Rindler is not the spacetime itself. It's the region. It's the entangling region. So yes. Here, the entangling region has nothing to do with Rindler. It can be an interval that is static, that is not doing anything. What is associated here to Rindler is the boundary of the spacetime.
Right, so, which is fixed by the moving mirror.
Yeah. So in that sense, it's a bit different to what they're doing.
Right.
But I think what I'm doing here is too simple to grasp, or at least I don't see how this knows about the information of the charges that gave rise to this black hole. It's something like this thing captures a more coarse-grained physics. This doesn't seem to make a difference whether, did you take a Reissner-Nostrom black hole that went to the BPS bound, or is it a Kerr, or is it something else?
Right.
Those sort of details, I don't think you can capture them with such a simple model. This is more related to like the causal structure of the space, of the extremal black hole. That's what I think.
Right. Okay. Thank you. So I have like another question. So right. So I mean, I don't have it so clear in my mind right now. But so the point is that okay, the mirror, right? The mirror. What is like its physical implementation, right? So I mean, do you consider, because the point is that okay, you say that it follows some let's say you consider the case where it moves in a time-like trajectory, right? In that case, it would be a material object with some finite mass, right?
Yeah.
But then you also consider the case where it has like a asymptotically light-like trajectory, right? Asymptotically null, right? So I mean, you cannot do that with a mirror that has a mass, right? Like you cannot, right?
Okay.
So right. So my point is that, are you considering some sort of probe approximation? Because you say that you're considering, I mean, you say that you want to take into account the back reaction in order to account for the radiation that the mirror would generate by virtue of its acceleration. So you're associating a charge to it in a way, right? But do you still consider if this mirror has mass or not? Because if you're considering,
absolutely yes, absolutely yes. So I kind of rushed through this, and I was not very explicit here in the slides either, but absolutely yes. So what you have to do in this problem, and this is basically what Chung and Verlinde did, it's a beautiful paper,
right?
Is that you need to solve two problems which are related, but you can solve them independently. But the solution of one is related to the solution of the other. So you have, on the one hand side, you have to solve Newton's equation for the point particle. Okay, so then you have to solve a differential equation. Now, which differential equation are you going to solve? Well, that depends. That depends on which field you're considering. So if the field is classical, so suppose I take a classical fermionic theory, okay, before quantizing it, and I couple it to this massive relativistic point particle. So then you have a system, it's basically like a string attached to like a ball at the end, more or less, that's the physics. So the waves can go, and there's going to be some interesting exchange of energy and momentum between the string, basically the wave, the field, and the ball, the particle. And you need to solve for both. So you need to solve F equals ma for the particle, and then you solve the wave equation for the field. But notice that this F, you need to, in order to solve this differential equation, you need to tell me what F is, and F is related to the loss of momentum of the field, right? That's the completely classical problem. And you can solve that, and it looks fine, actually. We looked at the solutions, and they look fine. The more interesting thing is that now you say, okay, we keep the particle classic, relativistic but classic, I mean non-quantum, and we quantize the field. So now we have this sort of quantum string or quantum field theory coupled to this classical point particle. And you still have to solve F equals ma for the particle. The difference now is that the F doesn't involve just the exchange of momentum with the field, but it grabs an extra term that comes from the fact that at the quantum level, the anomaly makes that you have this sort of Larmor effect, this backscattering. This is an extra sort of force that enters into the problem, which incidentally makes the differential equation for the particle a third order differential equation, which brings up a huge, it's a new field of physics.
The third order fact is just because of the Schwarzian derivative, no?
Yeah,
Okay.
yeah. I mean, in general, it can have different origins. Like in the case of classical electrodynamics, it's related to this Larmor effect, the power that is radiated. In our case, it's related to the anomaly.
Right.
Exactly. It depends a bit on the example that you're looking at. And then you have to solve the third order differential equation for the particle, which receives as an input the quantum or the expectation value of the stress tensor of the quantum field that is impacting it. And that's a super interesting set of equations to solve. The issue is that when you solve them, and there you see that the mass of the particle is definitely taken into account because it enters in F equals ma. And the issue is that you find these singular solutions. And as you said correctly, so if the particle, if a massive particle accelerates to the speed of light, then that's not good. Like that shouldn't be happening, because then you need an infinite amount of energy to do that. And that's already non-physical, but in these particular cases, it's even more dramatic because you start with a point particle that has a tiny acceleration at some point. And then what it does is that it starts, for example, in this case, it starts accelerating, receding from the system. And if you see here, it becomes asymptotically null. So it reaches the speed of light in like infinite proper time. But the system, if you're throwing in the vacuum, the initial energy of the system was almost zero. Like the particle is static, almost static. The field is in the vacuum state, so the total energy is almost zero. When the particle is very close to the speed of light, its energy is very high because the relativistic factor, the gamma factor, just goes to infinity. And it's positive because the energy of the particle is always positive. So what happens is that what this thing does is through the anomaly, it's throwing a huge amount of negative energy towards the universe. Moreover, there's these solutions where this happens in a finite proper time. So that looks more like the black hole singularity. It's like, your world line just ends at some point.
Right.
So, and in all of these cases, the mass of the particle is definitely taken into account through solving F equals ma.
I see. Okay, thank you very much for the answers. So
Thanks.
are there any further questions from the audience? Well, if not, we thanks again Ignacio Reyes for the fantastic seminar. So thank you very much. I'm going to stop recording.